Hello everybody, I would like to present another perspective of the phasors. In part 1 of this lecture, we define the phasor as taking the amplitude and phase angle of the sinusoidal signal defined by a cosine function. Right? There is another more mathematically rigorous treatment to the phasors, which is not presented in the text. So I would like to show you here, since this is a little bit more advanced topic for undergraduate course. So you are not required to watch this clip, but if you did, you're gonna receive extra credit for this. Okay, let's jump into the topic. And the phasor, we instead of doing just taking the amplitude and the phase angle, and we can define it as a formal transformation as shown here. So we integrate this sinusoidal signal multiplied by e2 minus j omega t over a fundamental period, which is a t related to omega as t is going to be equal omega over 2 pi. Okay. And let's check if this really works. We know the phasor of v should be equal to VA, since this is already a cosine function, and the phase angle should be the theta, right? So let's check if this integration actually really gives us this phasor form. First, let's recall the Euler identity. That's e2 cosine x plus j sine x. And then also, if you have a e2 minus jx, right? So you replace that x by minus x, you got a cosine x as well, because cosine is a even function. And for the sine, you get negative sine x, because the sine x is a odd function. So therefore, the cosine x, from this, you add these two equations, you get a 2 times, so e2jx plus e2 minus jx is going to be equal to 2 times cosine x. So therefore, if you divide both sides by 2, you get a cosine x equal to the sum of these two exponential functions divided by 2. And now we replace that vt by this the cosine function by these exponential functions. So vt in this case is going to be equal va over 2, and the cosine function there is e2 jx. Now we treat the whole thing as x, right? So e2 jx, which is e2 j omega t plus theta plus e2 minus j omega t plus theta. And now we substitute this back to the definition and see. So now we integrate this t over 2 and 0 to t. I just copy the whole thing here. And I just drop let me use the braces. And the dt. Oh no, we need to multiply by e2 minus j omega t and the dt. Right, you drop the whole thing here. And if we then we can multiply this out. So let's do another step. So this, I can factor this out because this is the constant. So I can factor this out, so I get VA over t, right? 0 to t, and this multiply out, we got e2 j omega t plus j theta, and minus j omega t, I got e2 j theta, because that the j omega t and minus j omega will be cancelled, and plus e2 minus 2 j omega t minus j theta. So this, we already multiply this out, and so this is dt, right? And this part, so we can break this integration into two integrations. And Vt over Va, V sub A over T, 0 to T, e to j theta dt plus Va over T from 0 to T, e to minus 2j omega t plus theta plus j theta dt. Actually minus. Although this doesn't really change the final result, but it should be minus here. And this term actually will give us a 0. The main reason for that is if you use Euler identity, you will end up with the real part as cosine 2 omega t, and the imaginary part as sine 2 omega t. So if you integrate those sine and cosine function over a fundamental period or integer number of the fundamental periods, and then you will always get a 0. So we only have the first term. The first term here, this is the e to j theta. This theta is constant, so therefore we can factor this out. So we have Va times e to j theta, and we have over t, and then what is left inside what's left as integrand, they be 1. So integral 1 over fundamental period t, you got a t. So the t and t going to be canceled, and you end up with Va times e to j theta. And this actually concludes the what we expected here. Right? So kind of simple proof. And this is mathematically rigorous. So what is it used for? And since this is mathematical, we actually can use the program. And I have a Python code to show you here. And this is the function. This is the function that I have 100 times cosine omega t plus pi over 4. So we know the polar form of the phasor should be 100 times e to j. The phase angle would be pi over 4, right? So if I use that rigorous definition, I can integrate the function, and I define the integrand and the real part of the integrand and the imaginary part of the integrand, and use the integration function called a quad in SciPy, the package, or the module. Then you can integrate. And if you execute the code, so the polar form of these, you have the phasor, and you have 45 degrees or pi over 4. So this actually will, you can check if you got a sine function that automatically take care of the phase angles. So if you have sine function that automatically will give you the phasors with the correct phase angles. And also I had a proof of the derivative property of the phasors using this more rigorous approach, and they approve which have very neat feature. You can get that. Check the notes. That will conclude this short video for this one. Thank you for watching.